We often think that modern science has erased creatures that were once thought to exist only in legends. But is it possible that scientific discoveries have accidentally revived a legend? People used to tremble before the image of giant sea serpents, endless sea snakes, wrapping around the ocean, swallowing ships. Leviathan in the Bible, Jormungandr in Norse mythology. For thousands of years, these were just folk myths passed down by word of mouth. But what would happen if 19th century scientists unearthed a giant skeleton that looked exactly like a legendary sea dragon? Were the ancient sailors really mistaken? Or did those legends preserve a faint memory of a creature that once existed? And more importantly, why would modern humans with microscopes and genetic maps make the same mistake as their ancestors? Give it a name, Basilosaurus, the lizard king. Only to find out it was not a snake, not a lizard, but one of the first ancient whales, an apex predator of the Eocene oceans. The question is, if Basilosaurus was not a sea serpent, why did it look so terrifyingly similar? If it was not a direct ancestor, why does it still leave traces in the bodies of whales today? And what made nature test a giant, powerful design, then wipe it out in just a few million years? Let's go back in time from myth to fossil to discover the secrets of the whale named after a mistaken king. Memory of a lost ocean. Millions of years ago, the warm oceans of the Eocene receded, leaving behind a barren world of sand and rock. Today, places like the Wadi Al-Hitan Valley in Egypt are vast natural museums, where the stories of lost life are written in fossils. This is not only a place that preserves ancient skeletons, but also a place that recreates a great age of adventure, where the first giants of the ocean rose after the mass extinction, and one of them bore a name full of confusion and mystery: Basilosaurus, the king lizard. The adventure of finding Basilosaurus did not begin in the Egyptian desert, but in the American South, specifically Louisiana and Alabama, in the 1800s. At that time, massive bone fragments scattered on a hillside were discovered after a heavy rain. A naturalist named Richard Harlan, when examining the vertebrae and jawbones he collected, reached a bold but seemingly reasonable conclusion at the time. Seeing the long, sinuous skeleton and its estimated length of 75 to 100 feet, Harlan thought it was the remains of a giant marine reptile comparable to the known large dinosaurs. This misunderstanding led to the name Basilosaurus, meaning king lizard. However, the true secret of Basilosaurus was revealed not long after, when Harlan's fossils reached Richard Owen, a famous British anatomist. With the sharp eye of a scientist, Owen examined the specimens and discovered an important anatomical detail: the double-rooted teeth characteristic of mammals, a feature impossible in reptiles. This discovery overturned the initial hypothesis, identifying Basilosaurus as an ancient marine mammal. Although Owen proposed renaming it Zeuglodon cetoides to reflect this truth, the rules of international zoological nomenclature still required keeping the original name to honor the history of discovery. The story of the name Basilosaurus is not only an interesting anecdote, but also a profound lesson about the scientific process. At first, with limited evidence, only a few vertebrae and jawbones, Harlan made a reasonable conclusion based on morphological similarities to known giant marine reptiles. But as more detailed data, complex tooth structure, became available, a newer, more accurate theory was born. The fact that the original name was retained is a vivid demonstration of how science works, always ready to change hypotheses with new evidence, but never erasing its own history. Decoding a monster. The appearance of Basilosaurus was far different from any modern whale. With an impressive length from 50 to 60 feet, some fossils even show it could reach up to 65 feet. It was a giant of the Eocene era. However, instead of the compact, torpedo-shaped body of today's whales, Basilosaurus had a long, slender, winding body, like an eel or a sea snake. This feature was the result of the unusual elongation of the thoracic and caudal vertebrae. Another unique anatomical feature is that its vertebrae, though long, were hollow and fluid-filled, unlike the solid, dense vertebrae of modern whales. This structure made its skeleton lighter and more buoyant, but also limited its ability to dive deeply, allowing it to move only up and down along the ocean's surface in vertical undulations. Basilosaurus had a relatively small and primitive brain compared to its huge body size. However, it compensated with a deadly weapon, its teeth. Its skull was crocodile-shaped, with large jaw muscle attachments, indicating a powerful bite. Its teeth included fang-like incisors at the front and molars with many sharp cusps at the back, capable of cutting, crushing, and piercing prey. This complex dentition, completely different from the simple teeth of modern fish-eating whales, provided scientists with an important clue about its diet and its position as an apex predator in the Eocene Ocean. To better understand the differences between Basilosaurus and modern whales, we can compare some key characteristics in the table below. These stark differences show that Basilosaurus was not the direct ancestor of modern whales, but rather a dead end in the evolutionary process. It was an example of a unique evolutionary path that nature tried in creating an entirely new marine creature. The secret doors of evolution. One of the greatest mysteries of Basilosaurus was decoded thanks to discoveries in Wadi Al-Hitan, Egypt. Complete skeletons found here revealed a shocking feature. Basilosaurus had tiny hind legs, only a tiny fraction of its body length. Their size was even shorter than a human arm. These legs, though small, had full joints and even toes. However, they were not connected to the spine, making them completely useless for walking on land or swimming. These tiny hind legs were not useless remnants, but important evidence, a clue that opened a new chapter in whale evolution. Scientists proposed a bold hypothesis. They may have been used as copulatory guides during mating. This hypothesis was reinforced by evidence that males had larger hind limbs than females. This is an extremely fascinating scientific detail, turning what seemed like a nonsensical feature into a key to the biological behavior of this creature. Basilosaurus represented an important transitional step. It had lost the ability to walk on land like its ancestors, but had not yet fully developed the reproductive adaptations of modern whales. The evolutionary journey of whales from land to sea is one of science's most astonishing stories, taking place over about 10 to 12 million years. From land-dwelling hoofed mammals, they underwent profound anatomical and physiological changes to become the fully aquatic creatures we know today. Paleontologists have been able to paint a detailed picture of this transition thanks to transitional fossils, especially in Pakistan, which was once an inland sea. Below are the main stages of this journey. Pachycetus, about 50 million years ago, the earliest known ancestor of whales. Pachycetus was a carnivorous land mammal resembling a wolf. It lived near the shores of a shallow sea and hunted fish. Though it looked like a land animal, its ear bones had unique whale-like features, the first evidence of evolutionary connection. Ambulocetus, about 47 million years ago. As its name means, the walking whale, this transitional form could move on both land and water. With webbed feet, it swam by paddling and undulating its body, much like today's otters. It could live in both freshwater and saltwater environments. Rhodhocetus, about 46 million years ago. This species showed a fully marine lifestyle. Its leg structure lost the ability to support its body weight on land and became better suited for swimming. Its neck was shorter and less flexible than land ancestors, an adaptation for swimming underwater. Basilosaurids, about 40 to 34 million years ago. The first fully aquatic whales. Though eel-like in shape, unlike the streamlined form of modern whales, they had deeper marine adaptations. Blowholes began moving backward on the skull. Hind limbs shrank and were no longer connected to the spine, existing only as vestigial appendages inside the body, unable to be used for walking on land. This evolutionary process included a series of major anatomical changes. Forelimbs gradually transformed into flippers for swimming and steering. Hind limbs shrank and eventually disappeared. Tails developed horizontal flukes, generating powerful thrust. Nostrils, blowholes, migrated from the snout to the top of the head, allowing easier breathing at the surface. Changes in jaw and ear bone structures allowed better underwater hearing. This rapid transformation is a powerful example of adaptation in response to environmental change. Basilosaurus was not the direct ancestor of modern whales, but a unique evolutionary branch, parallel to the lineage that led to smaller whales such as Dorudon. It is evidence that there were many different paths to becoming a fully aquatic marine creature, the traces of a predator. If there is a place on Earth that can be called a sanctuary of fossils, it is Wadi Al-Hitan in Egypt. Recognized by UNESCO as a World Heritage Site for its hundreds of fossils of early whales, this place was once a shallow sea, a natural nursery of the Eocene era. Hundreds of skeletons of Dorudon atrox, a smaller whale, have been found here, especially juveniles. This shows it was an ideal breeding ground for Dorudon, but also turned it into a perfect hunting territory for the ultimate predator. Basilosaurus isis. One of the greatest scientific discoveries took place here. A complete Basilosaurus skeleton was found with the remains of meals still inside its rib cage, where its stomach once lay. This groundbreaking discovery was the first and only direct evidence of Basilosaurus's diet. The bones found in its belly included at least 2 young Dorudons and numerous fragments of large fish. Scientists carefully analyzed these bone fragments. They were located within or just behind the rib cage of Basilosaurus, and notably, they bore clear bite marks on their skulls. The location of these bite marks showed Basilosaurus targeted its prey's head, a strategy identical to how killer whales, Orchinus orca, hunt young humpback whales today. The similarity in hunting tactics between Basilosaurus and modern killer whales is an incredible example of convergent evolution. Although not closely related, both species developed the same effective strategy for hunting large, mammalian prey. This shows that in ecology, some hunting strategies are eternal. Basilosaurus was not only a muscular predator, but also a cunning one, using efficient strategies to bring down its prey. The king among giants after the Cretaceous-Paleogene extinction event, KPG, wiped out giant marine reptiles such as mosasaurs and plesiosaurs, the ocean needed a new apex predator. Basilosaurus rose to claim this throne, becoming the first air-breathing apex predator of the ocean after the KPG extinction. However, that throne was not uncontested. The Eocene Ocean was a battlefield for power between 2 dynasties, ancient whales and sharks. At the same time as Basilosaurus, another formidable rival also ruled the seas, the giant shark Carcharocles auriculatus, ancestor of the largest shark of all time, C. megalodon. Although smaller than Basilosaurus, C. auriculatus was still a fearsome opponent, larger than modern killer whales and armed with razor-sharp teeth capable of inflicting fatal wounds. Many people often think whales seized the throne from sharks to become apex predators, but evidence from Basilosaurus and Carcharocles auriculatus shows these 2 dynasties coexisted and competed for millions of years. With its winding body and flexible spine, Basilosaurus was thought to be an efficient hunter in shallow coastal waters. Meanwhile, Carcharocles auriculatus likely controlled deeper waters. The Eocene Ocean had no single king, but rather a more dramatic, complex story of rivalry and adaptation between 2 groups of giant predators. The final legacy. The reign of Basilosaurus did not last forever. About 34 million years ago, a global climate event occurred, marking the end of the warm Eocene. Earth began to cool significantly, causing major changes in ocean currents and ecosystems. The warm, shallow seas that Basilosaurus was perfectly adapted to began to change. Its enormous size and specialized body, once an advantage, became a major obstacle as its habitat shifted. This change pushed Basilosaurus and other ancient whales into an evolutionary dead end, leading to their extinction. The death of Basilosaurus opened a new era for modern whales. The global cooling spurred diversification of toothed whales and baleen whales, species better adapted to colder, deeper oceans. Remarkably, even after millions of years of evolution, modern whales still carry within them the legacy of their land-dwelling ancestors. Their vestigial pelvis and hind limbs, hidden inside their bodies, are the remnants of legs that once helped their ancestors walk on land. These relics, along with the fossils found at Wadi Al-Hitan, have become undeniable evidence, a bridge connecting a 4-legged land animal to a giant gliding through the ocean. What seemed like a paradox at first has now been answered. Basilosaurus was not a sea serpent, but its long, sinuous form gave ancient people the illusion of a mythical sea serpent. The legends are not entirely wrong. They are simply a distorted memory of a real creature that once ruled the seas. It was not a direct ancestor of modern whales, but traces of it remain. Pelvic bones hidden in the bodies of today's whales. Reminders that they once walked on land before becoming predators of the ocean. And the natural reason that wiped out Basilosaurus is what makes evolution so amazing. Its massive body and unique structure helped it dominate during the warm Eocene. But as the climate changed, that advantage became a liability. The seemingly perfect design became a dead end. Science has given us the answer. The boundary between myth and reality is not a clear line, but a bridge. And Basilosaurus is that bridge between the millennial imagination of humans and the great truth that nature has written down in fossils. Perhaps we have only touched the surface. Nature still has more miracles than immortality. After hearing the story of Basilosaurus, which species would you choose to learn the secret of a healthier life? The slow and durable life of the giant tortoise? The ability of half-brain sleep and oxygen, storage of whales? Or the endless cell regeneration of the immortal jellyfish? And if you had the chance to live another 30 years, but in exchange you had to give up refined sugar or accept walking for an hour a day, would you be willing? Leave your comments below. We look forward to hearing from you. Don't forget to like, share, and subscribe so you don't miss the latest episodes.